박수로 맞으시면
올렸고요.
Miriam, so say hello to our participant and give a presentation, please.
Okay. Hello, guys. How are you doing today? Doing I hear you've had a interesting, fun conference. I'm glad you could all attend there in person. I'm sorry I cannot. It just did not work out with my work schedule and travel this time. But I'm excited to be here virtually. And I'm excited to speak to you. You said I'm Mariah. I'm a Go developer expert. I teach Go, I make Go videos, and I love speaking about Go. So this talk came about as I was preparing for one of the courses that I teach. I was building a course on web services, and my background is in physics. I have a degree in physics, so I didn't get a good computer science foundation before I started programming. So as I was preparing this course, a light bulb went off, and I realized that every operation that you do where you send bytes outside of your Go program, or you read bytes from outside of a Go program, uses the IO reader or IO writer interface. And like I said, I was building a web services course, so I was thinking, oh my goodness, every API call, every database call, every CLI call, all of these things are using IO reader and writer. And I just really wanted to understand a little bit more about these interfaces and how our bytes are moving from one place to the other. So, and also how to use them really, really effectively. So that's what we're going to talk about today. So this is a game. I can't see you, but you can see each other. So you can feel free to raise your hand. We have a game here in the United States called Never Have I Ever. And basically, if you have done something, so if this is something that has happened to you or something you've done, you're supposed to raise your hand. So I'm going to go through a list of things, and if you've done it, raise your hand, look around the room, see if your neighbors have done it as well. So, have you ever written a handler function for an HTTP server? Have you ever created an HTTP request for an HTTP client? Have you ever read from a SQL database? Have you ever read to or written from a file? Have you ever accessed an environment variable? Or have you ever accepted a CLI flag or an argument? If you've done any of these things, you've used either a reader or a writer that was implemented somewhere in the standard library. Like I said, they are everywhere. I don't want to show you that. Oops. So, everywhere. So what is IO? Like I said, this is for me because I don't have a good background in computer science, but IO is input and output. It is any kind of communication between our ecosystem, our Golang app, and anything outside of it, any outside system. So it could be to the local disk, it could be to a web server, it could be to a database, could be anywhere. That's an IO operation. So like I said, it's from inside the Go's memory to outside the Go app memory. So what do we use? We use readers. Right here, is the interface. It only has one method in it. It is the read method. It takes a slice of bytes, and then it returns the byte offset and an error. That's it. This is implemented all over the place. If you go to Tour of Go, it will tell you that this ends is the read end of a stream of bytes. So anytime Go is sending bits of data anywhere, it treats it like a stream, one continuous flow. It doesn't chunk it up, it doesn't do anything. Go always sends its data as a stream. So readers are the read end of the stream, writers are the write end of the stream. And like it takes data from the outside location, ingests it to another location inside that Go app. Here we have writers that has the write method. It takes a slice of bytes, writes it outside, returns an int and an error. Anytime in Go, I don't like to think of Go as an object-oriented language, but this is exactly how inheritance works with these writers. There are lots and lots of additional interfaces in Go that combine readers and writers in various forms. Sometimes it's reader writer, sometimes it's reader closer, sometimes it's reader writer closer. And so these interfaces that inherit other interfaces inherit both methods. So the read writer interface will require both the read method and the write method. The read closer will require the read method and the close method. So these are combined and used all over the place. You'll find that things like reader, writer, closer are very common in database instances or in file connections because you're typically doing all of those operations over a single connection. So how do you implement them? That's a good question. I hope you never have to implement these interfaces yourself. And why? Because they are implemented hundreds of times in the standard library. The reader interface is implemented over 300 times in the standard library. And the writer interface over 330 times. Just in the standard library, not database drivers, not third-party tools, not anything else. Just in their standard library, they're used almost 650 times combined. And what that means is that you really shouldn't need to implement it. I've never had to implement it, but I have used the implementations almost every time I write a piece of code. So how do you implement it? I don't know. We don't. We don't implement it. We just use the implementations. So great. We've learned about IO readers and writers. Now let's learn about using them. There's a couple of patterns in Go to write to and from memory. The two biggest ones are buffered IO operations and non-buffered IO operations. I'm sure you guys are aware. So what's the difference? The biggest difference is a buffered IO operation. Instead of sending a single large stream of bytes, it chunks it up into small streams of bytes. So it creates an intermediary array, both on the read side and the write side, and it will write those chunks of bytes to the intermediary array and allow for more granular error handling and more granular data protection if you need to have a finite control over how much over data writing or not. Like I said, when you do streams of byte writing, it's typically all or nothing. So if you're doing non-buffered IO, it's an all or nothing situation. But if you don't want to be in an all or nothing situation, using buffered ones can allow you to preserve integrity of a portion of that data. This right here is an example of just using a non-buffered IO operation. I just have a text file. It has Twitch chat from my Twitch stream. I stream Go programming on Twitch, and I just took a bunch of chat messages. We're opening that file. we're reading from that file, and we close that file at the end. As opposed to, oh, yes. When should we use this? We should use this when memory matters. Like I said, when you're doing buffered operations, you're going to write an additional array of data. So if you're trying to preserve heap space, you won't want to do additional writes. You want it to, it's a highly synchronous situation, right? It's an all or nothing. If it fails at any point, it immediately returns an error, as opposed to preserving a little bit on the inside, making it a little bit more asynchronous. Real-time events, this is perfect. Buffered operations, like I said, store data in memory before sending it out or before ingesting it completely. All buffered operations in Go use the buff.io module. So when do you use buffered operations? You're going to use them for optimized throughput, right? When you want to be able to handle little bits of the data at a time, as opposed to waiting for all of the data at once. You're going to want to do it when you want convenient error handling, when you want to be able to return an error during a partial failure instead of calling it a complete failure. This is an example. I did generate this using OpenAI's ChatGPT 3.5 because I was not thinking when I wrote this, but it works great. We're still opening the file using the OS open, but when we read it, instead of doing IO read, we're using the buff.io package new scanner, which the scanner then becomes that intermediary array. We scan the text, and then we return an error at the end. In this text here, I have a print line. When we go through our demo, there is not a print because in the previous one, we didn't have a print as well. So we got to keep our benchmarks accurate. Excuse me. Database I/O. I looked all over the standard library to figure out where the database was making its connections with readers and writers, and it was not in the standard library. It's in the third-party drivers. So the drivers themselves manage the data streams between the data store and the Go app. Often I've seen, when I was looking at the SQLite one, it did use copy, which also implements IO readers and writers. So it's in the open source drivers themselves. There are a couple of database systems that use Seago. So SQLite and DuckDB use Seago as well to manage reads and writes to the file, in addition to IO copy operations. Another thing to remember is that because databases use connection pools, it is very efficient to just do the IO calls on the data store itself without establishing a connection. And like I said, often these calls are using the the copy method. That's very efficient. Reestablishing database connections and closing database connections every time will be more inefficient if you're trying to do high throughput or high transaction system. This is a SQLite example, just because SQLite is the easiest to throw into an example repo. It has the same Twitch chat, about 10 lines, put it into a file. We open it, which is the part that uses Seago, that db.query, that is using the copy method, so that is an IO operation. And the rows.scan as well uses an IO operation. So, IO over the internet. In Go, when you're making calls over the internet, even though all the data is set as a stream chunked into packets, right? It's still a data stream, even though it comes in chunks and packets. We're using IO readers and writers. These are usually inside, well, not usually, are inside the HTTP write response and the HTTP request interfaces that we pull in our handler functions. Here is the exact method. When we do the HTTP header set, that is doing a write operation, and so does the fumped printf. That is also an IO write operation. We aren't reading anything in this example, but that's true. So now for the part that's the fun part. We've gone through a bunch of examples, but I said, great, how can we choose which one we want to use? Sometimes they're best generically, but can we really evaluate them numerically? And we can. So I have some Go code here. It's on my GitHub. Anyone can look at it. And all it is a couple of benchmark tests. So I've written some functions here in benchmarks Go. And this is, like I said, this is really fun. And they have a couple of methods for reading in. So we have we should go back to that. So we have a couple of files. We have a twitch.txt, right? Oh. This is the just some lines, about 5 lines of quick Twitch chat between my Twitch bot, which is an LLM bot, and a Twitch user. Really simple, easy to read in. We also have the Twitch chat DB, which is those same things again with the additional ID column. And then we have our functions. So we have several read functions, right? We have a read file. This is the non-buffered method. And then we have a buffered file. So we're going to start by comparing those. So right here, we have a benchmarks test, right? So we just have 2 benchmark functions. If you're not familiar with benchmark testing, they're really easy to set up. This n is essentially the number of times that it's run. We're going to specify a time frame, and it's going to run this as many times as possible within that time frame, the n. And then it's going to run this function, read all file. And then it's going to also run the function read file buff. It'll then tell us several metrics that are the average, or, well, I guess technically they're the mean, based on the mean, the total number of runs, the mean time per run, the mean number of bytes allocated per run, and the mean number of heap allocations made. So these are calls to the heap. When I run them, go test, benchmark, I always turn on bench memory true because I like to see the memory statistics. And then the other thing we're doing is we're making our time limit be 10 seconds. So it's going to run as many times as it can in 10 seconds, or the total of 100 million times, or 1 billion times. I don't remember what the max is. So it's going to take 10 seconds, and we're just running 2 of them. So this is the read all file benchmark. And like I said, it takes 10 seconds. I'm sorry. So here we can see that it's run 1.5 million times. It takes about 75,000 nanoseconds per operation. 630 bytes were written per operation, and it takes 4 allocation methods. When the read buff, right? So this is the buffered one. The number of runs, it's about a little over 10 million less. The amount of time it takes is almost identical, but the number of bytes is about 10 times more, an order of magnitude more. So if you were choosing to do non-buffered versus buffered, and you don't care about error handling, returning early, anything like that, I would suggest looking at memory and notice that this is going to take up a whole lot more memory. Another thing that's good to know. So, okay, we got more. I've got more of these to look at. So, this one right here, read file. We're going to put this right here. So, here I'm doing an OS open and then an IO read all. But there's also a function in OS that just reads the file for you. Oh, look at you guys. I just got a picture. So here, it does the open, it pulls it in, it does a size, it makes a slice of bytes, appends the length, it does all this fun stuff, right? I don't really know what all that stuff is because writing a language is scary to me. But I figured whenever I am writing Go, this right here, this open and then IO read all, this is what my AI assistants tend to suggest to me, whether it be GitHub Copilot or Gemini, whatnot. They always suggest these two to me. But this is fewer lines of code. And so I said, well, let's test it. Let's see what the difference is. So we can go ahead and run that here. I'll just uncomment that. We don't need the buffered one. Right? Let's test this. It'll take 10 seconds again. I am sorry that I cannot speed that up. But it is way more fun to run it live. Way more fun. Oh, I bet I just did a stupid. 1 minute. So, I'm back. I apologize for that. I refreshed the browser. But what's a talk without a few technical difficulties, right? And it's not going to be in the demo because my demo is flawless. It's a little bit of American sarcasm for you. So, like you see, we have the IO read all and then the read file. Notice time's about the same, right? About 1,000 nanoseconds off. I can't notice 1,000 nanoseconds. But it does, interestingly enough, the OS does write, again, an insignificant amount more of bytes. So I find that funny, that even though I would say about 200 bytes is insignificant, the implementations perform differently. And this is consistently higher. So I have more. So let's look over here. Has anybody ever thought at another great, not anybody ever thought, but let's talk about this right here. I have these three right here that are great. Again, code editors. Whenever I need a new bytes buffer, I need a buffer, right? So if I'm writing an HTTP response, or I'm writing an HTTP request and I need to send JSON, or I need to just send a string, it almost always casts it, converts it, that string, from a string to a slice of bytes. The code assistants almost never say, hey, use a strings new reader. Never. They always say, use a bytes reader. It doesn't make sense to me, but we could be using a strings reader, right? So here we're going to do a strings reader and we're going to read it into a buffer. And here we're going to do a bytes reader and then read it into the same buffer, right? And then we'll try this read from one too. So here's an interesting method. So go doc. Are there any Vim users out there? My new favorite command is go doc. I don't know why. So read from. Read from is also fun because instead of passing the slice of bytes like I was doing before, I can pass the IO reader itself. So let's compare the reader, the string reader and the string writer, and then we'll compare the bytes from after. Okay. We'll pull that benchmark test over. We don't need you. We don't need you. Where's our string reader and byte reader? There they are. Okay, so string reader is going to do a strings new reader, and the byte reader is going to do a bytes new reader. But their original data is a string for both cases. Right? It's this string. Sorry, I didn't show you the string. It's this string. This string was generated again by code editor. I just kept pressing tab. So let's go ahead and run our benchmarks on that. Oops. I do this a lot. I forget to comment all the right things. Where was it? On line 27? See? I forgot to comment that. Okay. So this one, we're testing the strings.new reader buffer first. Look, this is the maximum number of times it can write. This is how many zeros? 1, 2, so 1 billion times. In in Spanish, they don't go from 1 million to 1 billion. They do 1,000 million. So if that's how it works in Korean, I apologize for English numbers. So this strings reader ran the maximum number of times. It took 4 nanoseconds per operation. It did no writing to the heap. Now that's what's impressive. We did not write one single bit to the heap. Whereas the bytes writer, it did not run the max number of times. It only did 300 million times. It took 35 nanoseconds per operation, and it did write to the heap. Why is that? Because Go doesn't cast, it only converts. So it had to take that string, write it to an array of bytes, and then send that array of bytes to the buffer instead of sending the string right to the buffer. So the compiler takes care of all of the legwork. If we use strings reader, and if we do bytes reader and we cast the byte to a string, or we convert the bytes to a string, the compiler doesn't take care of that for us. Okay. The next one I want to compare. So byte reader and then byte read from. So here we have a bytes reader, 2 things, but here we're using 2 different methods. We have read versus read from. So here with read, we're acting on the reader itself. But with read from, we're acting on the buffer. So in this case, we pass in the buffer and act on the IO reader. And in this case, we act on the buffer and pass in the IO reader. It's kind of funny that we have juxtaposed or replaced methods in that case. So how do they compare? 10 seconds. I mean, we could have done 20 or 30 seconds and had a much larger sample size, but that wouldn't be as fun or as quick. So this case, right, this is us acting on the reader and passing in the buffer. We do some 1 write to the heap, 128 bytes, much quicker. But when we read from an IO reader, look how much longer it takes in this instance. Now, this is not always the case. Now, these read from behaves differently if the source is external. So, in this case, where we're just writing a string, it is much more efficient to do read on the IO reader than it is to do read from on the buffer. Isn't that fun? Okay. So I want to talk about some of these write options a little bit. We're going to start here with copy. So we have copy and bytes writer. These both take string. And like I said, copy is used all over database stuff. And it is probably the only IO operation that can operate internal to the Go ecosystem, right? So we're reading from this string, we're writing to this buffer, and those are all internal to our app. Now, if our buffer was an external file, we could also read from one file and write to another file, or we could read from a database and write to a file, or something like that. We can do it on lots of things, but it can also be done internally. As opposed to this, where we're just writing to a buffer, right? So in both cases, we're writing this test string to a buffer. We're just using IO copy or the write method, and we're going to compare those two. So we don't want these two. I apologize for yawning. It is early morning for me. So I am ready for my good night's sleep. Or good morning's sleep, whatever works there. So this is, again, just taking a slice of bytes that was once a string and writing it to a buffer, an internal buffer. That's all it's doing, and it's using the write method on the buffer. Oh, did we not comment out the other one? Oops. Where's our commented? Oh, we did run IO copy. Did that not run? Copy didn't even run. What did I do? IO copy. Well, it ran once. Interesting. And it's capitalized, so it should have run. I don't know why it didn't run. I must just try it one more time. If not, you can test it on your own, and I'll move on to my last demo. And then we'll have time for questions after my last demo. Okay, it's not doing copy. I don't know. It has done it in the past for me. So the last one, we're going to do file write. Just because we already did the read, right? This has an OS write file, and this is doing the open and then the write method. That's pretty much it. Very simple. Go test. So this one is the file open, where we have one line that opens the file and a second line that writes to the file. And we're just writing that test string from above, nothing complicated. It does allocate to the heap before it writes. And that's probably the conversion from string to slice of bytes. But notice OS file, like that single line, takes again more than double the amount of time. I don't know why a single line operation takes more, why the compiler doesn't iron that one out, but it's the case. So if you care about saving nanoseconds of time, doing it this way is faster. If you don't care about that, the os.file write is much simpler. So in summary, oh wait, we got to go back to this screen. Oops, in summary, every Go app will use I/O operations at some point. It will interact with the ecosystem outside, and it will do I/O operations. There are lots of implementations of the I/O reader and writer, so many you will most likely never have to do it yourself. And then we learned what kinds of operations they have and how to evaluate readers and writers. So now we're going to open for questions. I just want to remind everybody, my name's Mariah. I am a Go developer expert. I live in the United States in Utah. I speak on Go. I stream on Twitch and YouTube about Go. And you can find me on Twitter, on LinkedIn, or and look at any of this code on GitHub. So if you have any questions, let me know. Go ahead. I think we're posting them in the Slido thing, and then they will be translated and sent to me, because Korean is not one of the two languages I speak. I speak English, I speak Spanish. Haven't learned Korean yet. Okay, so I'm going to join the Google Meet room. Join that. Should I stop sharing my screen?